Welcome back to the tutorial section of the morning. After Tathagata's talk, TD's talk. So this is TD. He'll be talking about Spark Streaming. He's the lead on the Spark Streaming project and a grad student at Berkeley. After his talk, we'll be breaking into the hands-on exercise section. During his talk, near the end, you'll receive an email from me with your login information and keys that you'll use during the hands-on section for getting into your Amazon cluster that we've already spun up for you. The email will be a little bit concise about what to do with the key files that are attached. It'll also have a link to the exercises, which we just published onto the Spark Summit website this morning. And inside of the exercises, there are more detailed instructions for what you need to do with the keys that are attached to the email. So let's let TD give his talk. You can learn about Spark Streaming, and then I'll see you again when we start the hands-on exercises.
Thank you very much, Andy, for the introduction. So Spark Streaming. As you have already heard a number of times in yesterday and today, that Spark Stream is one of the key components of our stack, and it extends the Spark batch processing system to do stream processing. The project started as a research project early 2012, and then we built it, and the alpha version of it was released spring 2013 with Spark 0.7. Right now in Spark 0.9 coming January, we are going to move it out of alpha. Even though it has been alpha, it has been fairly stable, and a lot of people have been using it already. So let me start with the motivation behind building Spark Streaming and why we built it. And we basically looked around and we saw that there are many big data applications that need to process large streams of data in real time. For example, website monitoring, where you want to monitor the load on your website, or fraud detection, where you want to, as soon as possible, figure out from a stream of transactions, or bank transactions, figure out whether there's a fraud or not. Or ad monetization is one of the very common examples, is counting the number of clicks and taking the decision based on which ads are more popular, etc. Now, the common thing across all these applications is that for a framework we need a framework to build these applications that can scale to hundreds of nodes, achieve second scale latencies, and efficiently recover from faults and node failures, and very importantly, integrates very nicely with batch interactive processing. And the first 2 points are kind of obvious. It's big data after all. And let me elaborate a bit on the next 2 points and why we thought that the second 2 points are very key, and we should make that one of our goals. So we found that many of the environments, starting with one key example would be Conviva. Many of the environments that process live data streams also take the same data and do batch processing on them as well. Let's say to take the same data and generate monthly, yearly reports on the same data. Now, the problem with building this kind of systems is that there is no single framework that can do both this kind of stream processing and batch processing together in the same platform. It did not exist until now, and so either people use Hadoop for doing their batch processing on petabytes and terabytes of data, but it has high latency, or people used something like Storm to process data at the rates of 100 megabytes per second with low latency, but no single system could do both. So, and as some of you have already seen in yesterday's talk from Conviva, that it is extremely painful to maintain these 2 different stacks, because it increases your code size by twice, sometimes more than 2x. You have to deal with different programming models in these 2 different stacks, and therefore understand the idiosyncrasies of each model, and increases the development effort, increases the number of bugs you need to fix, etc. In short, it's not fun. That's point one. The point two is that often we want to do stateful stream processing. For example, let's say you want to count the records that you have received, the number of tweets, let's say you have seen over a period of time. And for that, you need to maintain some state, which is basically the count, which you keep incrementing as you see more records. And traditionally, the stream processing systems have done it in a kind of similar way, which is basically they set up a pipeline of nodes which will process the stream. Each node maintains an in-memory mutable state, which in this case is the count. And as the input records come into the node, it updates the mutable state. In this case, increments the count, and the maybe transformed records are sent out downstream to the further into the pipeline nodes in the pipeline. Now, the problem with this mutable state is that if the node dies, that mutable state is lost. And so making this mutable state has always been a challenge. And traditionally, different systems have taken different approaches from replication, etc. I will not go into the details of all these possible approaches, but I will touch upon approaches taken by some of the more popular systems, like, for example, Storm. So what Storm guarantees is that it will replay any record if a node has not processed that record, which means that it only guarantees at least once processing. So every record will be processed at least once, which also means that if you want to maintain a count of records, you can easily get double counted because a record may be replayed twice. You will never know. And the mutable state, the count, can be easily lost when one of the node fails. To deal with this limitation of Storm, Trident was built on top of Storm, which used transactions to an external database kind of system to update the state so that it gives you the exactly once property that every record will be processed and the state updated by that record only once. But doing this per state transaction to an external system obviously causes a reduction in throughput that has been reported by many developers. So, and with these motivations, we built this system, Spark Streaming. And the key idea behind the way Spark Streaming works is actually very simple. We essentially take a streaming computation and divide it into a series of very small deterministic batch jobs. Let's say we have a live data stream. My mic's off. It's on. And now my screen is off. Okay, Murphy's laws hit me. Yes, where was I? So yes, so the basic idea is that let's say you have a live data stream coming in. What Spark Streaming will essentially do is divide the data into batches of X seconds. This X is configurable, and typically it's few seconds. And forward those batches as RDDs to Spark. Spark will essentially process those RDDs and give you back the processed results in batches again. Now, the challenge is that whether can we reduce these batches, the size of the batches to as low as possible so that to ensure that the end-to-end latency is of the order of few seconds. And yes, we can. We can reduce the batch size to as low as half second, sometimes even lower, to get end-to-end latencies of 1 second. And since it's built on the Spark platform, it is natural that there's a huge potential of combining batch processing and stream processing within the same framework. That was the premise that we started with. And we developed Spark Streaming, and let's see how a Spark Streaming code looks like. So let's say you want to process the live Twitter stream and get a stream of hashtags from that Twitter stream. And the way you would do this is, first of all, you create use the API to create this variable called tweets, which is essentially a D stream. And dstream is basically a higher level abstraction over RDD, and essentially it's a sequence of RDDs representing a stream of data. And once you create this dstream, essentially what the system underneath will do is that it will chop up the data into X second batches and make RDDs out of them and keep them around in memory in the Spark cluster. Then you apply some sort of transformation. In this case, we are doing a flat map where from each of the tweet status, we are getting the list of tags from the status. And this essentially creates a new dstream, hashtags. And underneath the system will take every tweet's RDD and apply the flat map operation and generate the hashtags RDD. Finally, after you have done all your transformations, you can use what we call output operations to save the data, the transformed data somewhere. In this case, let's say you want to save it to each transformed, the hashtag RDDs to HDFS. You can apply the save as Hadoop files, give it a HDFS path, and the system will automatically save every batch of hashtags to HDFS. And not just HDFS, you can do anything you want with the data. For example, this for each operation, what it will allows you to do is it will give you the hashtag RDD, and you can do anything you want with that hashtag RDD. And people have done various different things. For example, if you were at the share through talk yesterday, productionalizing Spark Streaming, what they have done, they have leveraged Twitter's Storehouse platform to push these hashtags data into a Redis store. And Storehouse has other stores as well, so you can basically combine, leverage other existing code to push your data out to Redis store, Cassandra, etc. Or you can directly update your website as well. So this for each is again another output operation. And to give you an idea that you can directly push it out to a website, let me show you a quick demo that I have been running. So this is, okay. The internet has been acting weird, so I'm not sure whether I'll be able to show this properly. But this is.
Can you reposition the window a little bit? It's a little bit off the side of the.
Yes, there you are. And is the text visible? Okay, I got the answer. So this is the actual Spark streaming code. To walk through the code a little bit, first you need to do basically a little bit of boilerplate to parse the main arguments. By the way, this is in Scala. You can also write the same code in Java. Similar to the Spark context that you see in Spark, you create a streaming context with all the information. Here, I'm creating multiple tweet streams out here, just like the tweet stream I showed in the slides. Here, I'm applying this exact flat map operation, and then I'm doing a few more operations on this that I will not go into in detail. You're actually going to write this exact same program in your hands-on tutorial, so you will get a step-by-step instructions of what each of this line means. I'm just giving a very high overview, and finally, what I'm also doing is this tag counts, which is basically the count of the hashtags, and I'm calling print on it. What print essentially does is that it is an output operation that prints a sample of the data present in each of the transformed RDD. And that I'm also essentially pushing this data out to a website, which is this. And again, yes, yes. And so what that program essentially does is basically it counts the frequency of each hashtag over a window of time and sorts them and gives the top most popular hashtags. And as you can see, there are MTV stars. Well, I don't know whether you can see. Let me zoom it a little bit. This is what people are talking about. People's Choice, apparently People's Choice 2014 vote has been opened today. That's why people are crazy about it. Something about MTV stars, female artists somewhere, etc. It's often fun to actually look at your personal. It's like my personal trending topics on Twitter. Anyways, back to the talk. As I said, the same example also works in Java. We actively maintain the Java API as well. So those who don't want to jump into Scala can also directly use the Java API. What we do not have is the Python API yet, but we will have it. It's in our roadmap. I already talked briefly a little bit about doing computations over a window. Essentially, the window is an operation that is provided in the dstream API, and is essentially kind of defines this moving sliding window over the dstream of data, and it is defined by two parameters. One is the length of the window, and the sliding interval. So basically, you can in this case, you're specifying that give me the count of the tags every minute, every 5 seconds over a last 1 minute window. This is what essentially does. And there are other window-based operations that I will not go into the detail. You can take a look at the API docs and the streaming guide online. But it's interesting. What I will highlight is that this sort of window-based operation is something that other streaming frameworks like Storm does not provide out of the box, but we do. To go a little bit into a few of the interesting dstream operations that are there, what you can also do is maintain arbitrary per key state in which gets updated by every new data. For example, if you want to, let's say, do something creepy, that for every tweet, for every user out there, you want to maintain what mood that user in based on what that user is tweeting, then all you need to specify is a function, in this case update mood, where you specify that given the new set of tweets that the user has made and the last mood, what is the new mood he or she is in. Then you use this transformation update state by key to specify the function, update mood function. The system will generate a stream of moods, which is basically a stream of states that the system will automatically keep updating. Another interesting operation is transform, and this allows you to arbitrarily combine batch and streaming computations together in the same streaming program. So you can do something like, so what transform allows you to do is specify an arbitrary RDD to RDD function and apply it on a D stream. So for every RDD in a D stream, in this case, let's say you want to take the tweets D stream and filter the tweet D stream by some spam an HDFS file of spam hashtags, so that you want to filter out spam from the raw tweet D stream. And what you can do is apply the transform function, take each of the tweet RDDs and join it with the spam HDFS file, filter it, whatever you want with it. And this is very powerful because you can do any kind of batch processing kind of stuff in the middle of the stream processing computation. And people have been actually using it for doing pretty complex kind of stuff. In fact, this combination of views of dstream and RDDs, this together is very powerful because it allows you to do a lot of complex different things. Like, for example, people have been doing online machine learning where you have people just reuse their existing, let's say, k-means code that they have written for batch processing and just put it in, use transform to put it inside a stream and just have k-means running on streaming. And people have done that. It allows also to combine live data streams with historical data, basically generate a compressed form of historical data by running some external jobs on Spark, for example, and use that data to filter out the live data stream. Also, people have done CEP-style processing, where you take the window-based operation and do filtering on the whole window and things like that. Out of the box, we provide multiple different input sources: Kafka, HDFS, Flume, Cactus, raw TCP sockets, and there are others. And it's very easy to write your own data source. People have been actively doing that. And not just your own streaming data source, what you can also do is generate your own RDDs, let's say using GraphX or Shark or etc., and push those RDDs as part of a stream. And the system will automatically treat it as a stream and apply all the streaming computations on top of this sequence of RDDs that you generate from wherever you want. To go back and talk a bit about fault tolerance, how we deal with faults. So a very key property of RDDs is that each of the transformed RDD, in this case, let's say the hashtags RDD, remembers how it was generated from its previous RDDs. So to achieve fault tolerance, what we do is that the raw input data is replicated in memory in the Spark clusters, and all the transform RDDs point back to that. If one of the Spark worker nodes die and a part of that cached RDD is lost, it will recreate the system will automatically recreate the lost partitions in other machines because it knows this lineage information and recreate based on that lineage. And because of this inherent property of RDDs, the system automatically gives exactly one's property to all transformations, and you don't have to worry whether the workers failed or not. And this is what sets it apart from things like Storm. Let's talk about performance. We have tested Spark Streaming, and we can process 60 million records per second. That was about 6 gigabytes per second of live text data streams on 100 nodes, all with end-to-end latency of 1 second. The graph shows that the throughput of the whole cluster increases very linearly with respect to the size of the cluster. So you can see that the whole system is very scalable. And we tried different simple workloads for this particular benchmark. grep in this case is basically filters the text stream, and that is essentially what we can process 60 million records per second. Word count is slightly more complex, where the throughput is slightly lower because it's doing more work, obviously. We also compared it with other systems. We actually compared it with Storm, and we found that our throughput was higher than Storm, but then the Storm probably has improved its performance over things, so it's a moving target essentially. But the throughput essentially is comparable, and we also to compare with the reported numbers of other commercial streaming systems like Stream Inside, Oracle stuff, we are in the comparable ballpark of 100 to 500,000 records per second per node. And system, because if it's fast, because all the data is in memory and it can recompute lost partitions from in-memory data really fast, it can recover from failures within seconds. And this is what this graph shows, is that this is the time to process every batch of data. And when there's a failure, the subsequent batch takes a little longer to recompute lost data, but it recovers pretty fast and then continues as if nothing had happened. We also tried more complex applications. For example, the mobile Millennium project is a research project back in UC Berkeley, where it uses GPS observations GPS observations to estimate traffic transit times using online machine learning algorithm, in this case, Markov chain Monte Carlo simulation on GPS observations. Please do not ask me what that is. I did not write it. But at a high level, that is very CPU intensive, and so it requires a large cluster to do any useful kind of processing. And as you can see in the graph, that the program scales pretty nicely with the number of nodes in the cluster. But another interesting thing about this project, this attempt to streamify traffic transit time estimation, was that it took a single developer 1 to 2 weeks to come up with the streaming version of it, because he already had the batch processing version of doing Markov chain Monte Carlo. All he had to do was take that code and stick it in within the dstream interface, and almost with very little effort, he got it running to run on live data streams. And that is essentially the power of unification that we have. So what you can essentially do is combine interactive processing, batch, and streaming together. So let's say you have your customers are reporting a new kind of error that they are seeing in their logs. What you can do is first use Spark Shell or PySpark's Python shell in PySpark to interactively explore the data to identify where the problem is. Then you can take the same code, essentially the same code, and stick it in a standalone Spark program and run it on terabytes and petabytes of logs. Also, you can take the same, very similar code and stick it within the dstream framework and run the same algorithm within Spark Streaming to do the same getter identification in real time. And this is the advantage of having a single system being able to do everything. And you have already heard Michael talk about that you can create RDDs from Shark and stick it in Spark, Spark Streaming, etc. So all that comes out of the box because of this unified stack. Finally, let me talk about our roadmap. So Spark as 0.7 was the first release, the alpha version, and that was early 2013. Even though it was alpha, it has been fairly stable because it is built on top of a very solid base of Spark, which has been stable and really performed really wonderful. So since its underlying core engine has been stable, Spark Streaming overall has been stable, and people have been using it actively in production, even though it has been alpha. The main reason we called it alpha because the master fault tolerance in a Spark Streaming system was involved manual recovery. Basically, what Spark Streaming does is it checkpoints all the necessary information of the streaming computation in an HDFS file. You can manually recover the streaming computation from that HDFS file by manually restarting the streaming computation. But in Spark 0.9, which is going to be released in Jan 2014, we are going to fix that. We are going to automate the master fault recovery, and therefore we're going to get it out of alpha. We're going to have a lot of performance optimization, especially in window-based operations. Also, we are planning to include a different web UI just for Spark Streaming, so that to give higher level information beyond the web UI that you saw for Spark, to give higher level information like what is the delay in the system, etc., that is not evident in just the Spark UI. In the longer term, we have, in no particular order, we have goals for extending Spark Streaming to the Python API, extending MLlib, which is, to remind you, it is a set of machine learning algorithms like k-means, etc. for Spark, extending it to run in Spark Streaming. And also, as you can see, since both Shark and Spark Streaming is built on top of Spark, there's a huge potential for extending Shark to the streaming side as well, Shark Streaming. We rely on community to give us feedback for prioritizing these goals. And so for those who have been using Spark Streaming, please come and talk to me. I have been talking to people to understand what the problems they're facing, etc. And it helps us to prioritize our goals. And obviously, contributions are immensely welcome. Feel free to talk to me, ping me, email me directly for any kind of discussion. One final slide about today's tutorial. So one key thing about today's tutorial is that you are going to process the tweet data stream in the example that I demoed. You're going to exactly write that example. But to be able to do that, you need to have a Twitter account, and you need to generate authentication keys using that Twitter account. Those keys are needed for you to access the tweet stream. All the instructions are in the tutorial, so you don't have to worry. But the key thing to remember is that your Twitter account is not at risk out here, because at no point of time you have to enter your Twitter account password. You just have to use the keys that you generate on the spot. And once your tutorial is over, you can destroy the keys and everything will be safe. So that is not a concern. Finally, to conclude, all the information of the stream, how to program using these streams, are there on the Spark website. And if you are interested in going a bit deeper on how this works underneath, you can take a look at our research paper. This is the short paper version. There's also the long paper versions that was published in SOSP. You can Google it and take a look. Thank you.
Time for a couple of questions.
Yes, sure.
Wait, you need a microphone.
Yes.
How long is the raw data kept around for fault tolerance? Like you said, if you lose a node, it regenerates from lineage.
Very good question. The data right now in Spark 0.8.1 is kept around until the Spark's natural LRU kind of throws away the data. But with Spark 0.9, we're going to actively throw away the data to minimize the memory usage of Spark. And the system automatically keeps track of how much data is necessary to ensure fault tolerance and things like that. And accordingly, it will throw out data that is not needed anymore. There was somebody else here. Same question. Okay, cool. Yes. Oh.
So I'm curious, as far as with the transformations, I could imagine that you might have multiple incompatible transformations with like a windowing operation. Would you how would you set that up? Would you set up multiple windows off of a core RDD and then run different transforms against them? Or you look like you're not following the question.
I'm partially. So if you have, as far as I understood your question, if you want to do different operations over different windows with different, let's say, moving intervals and things like that.
No, I meant more like the same. Let's say you have the same windowing time frame you wanted, but you want to do multiple different transformations. Like one would go to k-means, another would go to something else. What's the optimal way to do that? Do you use the same underlying RDD to set up the stream, or do you set up different RDDs?
Yeah, so the abstraction here is D streams, which is a sequence of RDDs. So just like you can use in Spark, you can use a single RDD for doing multiple transformations. You can use a single D stream to do multiple transformations on top of them, and all of those will be computed in parallel. Does that answer your question?
I think so, but I don't understand how wouldn't windowing affect. Each one has its own windowing operation then?
You can have each one as a windowing operation. Yes, you can. Yeah. Okay. That was a simple answer.
My question is regarding persistent layer. Is HDFS the only way? That's my number one question. Number two is persistent automatically done or must be manually triggered?
Okay, so for the first question, in the current Spark 8.1, writing the data through HDFS, since we do not have the full automated master fault tolerance, to ensure no data loss, HDFS is the only way to ensure no data loss, but in 0.9 that is going to change, so that will definitely improve. And that's just a month away. That's answer for question one. For question two, for D-stream operations like updating the state where it is inherently going to reuse RDDs, the persistence level is automatically set. But for operations where you want to do multiple transformation on the same D-stream, there you are like kind of reusing the D-stream over there. For that, the developer needs to set the persistence level explicitly. Kind of like RDDs where you set the persistence levels of RDDs that are going to reuse. It's essentially the same thing.
Yeah, my question is, how do you calibrate your stream capacity requirements? Obviously, if you're just doing aggregates on a Twitter stream with the bird dog level access, the requirements are much smaller than the full fire hose. So how do you understand, how many partitions you need, making sure your aggregates will fit in each partition, and just sizing those requirements?
So that is essentially the same problem that is with any map reduce based system. You need to figure out the right number of reducers, etc. So Spark has some optimizations which automatically sets the number of reducers correctly, not correctly as in optimistically and stuff. So there is no magic answer to this. That is something you need to play around and try it.
The question was, if you haven't provisioned enough capacity, do you drop data?
So you can set the persistence level to drop data to local disk. So if you don't have enough capacity in the memory, you will drop the data to local disk, and so which can be read back again. But that will obviously harm the throughput in the long run. So yes, to have low latency, you need to have enough provision in the memory so that all the data necessary is present in the memory. Yes.
Hi. I understand the batching of the disk stream is based on a time period.
Yes.
What if for a certain period of time you get no data coming through the stream? How do you handle that? Like, do you generate empty RDDs or how?
Yes.
Okay.
Empty RDDs.
Okay.
One question. If, for instance, I have a queue that contains a lot of messages, and all these messages have their own timestamp, can I actually use that timestamp to do the timing of the D stream?
Right now, there is no easy way of doing that. But if you want to use those timestamps to do windowing on, for doing windowing on using the application level timestamps, the recommended way of doing it is which allows you to handle delayed records based on that application timestamp is have a D stream level window slightly bigger than the window that you want, and then filter out the records based on that window. It's not semantically very clean, but that is the way to do it, and some people have done it that way, yes. But there is no current automated support for that. By the way, I will still be around during the tutorials, so you can always come and talk to me. I think we're done. Okay. Thank you very much.